Hello students, today we start the session Thermodynamics. Thermodynamics is the interrelation between heat and mechanical energy. Here we study the interior of the system and describe it in terms of macroscopic quantities which have a bearing on its internal state. These macroscopic quantities are called thermodynamic coordinates or state variables. Such coordinates serve to determine the internal energy of the system. The system by which these coordinates describe is called a thermodynamic system. The equation of state is a mathematical function connecting the appropriate thermodynamic coordinates of a system in equilibrium, and the equation of state expresses the individual behavior of the system. Next, thermodynamic equilibrium. When a system in a state of thermodynamic equilibrium, the system should possess three conditions. First one, the system should possess mechanical equilibrium. Second, the system should possess chemical equilibrium. The system should possess thermal equilibrium. Then what is mechanical equilibrium? When there is no unbalanced force in the interior of a system and is none between the system and its surrounding, the system is said to be in a state of mechanical equilibrium. In the mechanical equilibrium state, the system there is no force in the acting in the interior part of the system. Next, chemical equilibrium. In chemical equilibrium, the system in the system there is no chemical reaction in the interior part of the system, or there is no transfer of energy from one system to other. Then thermal equilibrium. In thermal equilibrium, all part of the system are at the same temperature. That is, there is no temperature difference between the system and the surroundings. When the conditions for all three types of equilibrium are satisfied, the system is said to be in a state of thermodynamic equilibrium. States of thermodynamic equilibrium can be described in terms of macroscopic coordinates that do not involve time, that is, in terms of thermodynamic coordinates. Thermal equilibrium and zeroth law of thermodynamics. Here comes the zeroth law of thermodynamics. Here in order to describe zeroth law of thermodynamics, we have to consider a system of constant mass and composition, and each requiring only one pair of independent coordinates for its description. Here we use the symbols y and x for a pair of independent coordinates. A state of a system in which the coordinates y and x have definite values that remains constant so long as the external conditions are unchanged is called an equilibrium state. Existence of an equilibrium state in one system depends on the proximity of the other system and on the nature of the wall separating between them. That is, the walls are said to be either adiabatic or diathermic. Here the figure shows two systems, system A and system B. Here system A is separated by the system B by means of an adiabatic wall. Here the dashed line shows the adiabatic wall. Adiabatic wall, here the system A, all the values of x and y are possible. The two systems A and B are separated by diathermic wall. In diathermic wall, only restricted values of y and x are possible. Adiabatic wall. If a wall is adiabatic, a state y and x for a system A and y dash x dash for a system B may coexist as equilibrium states for any attainable values of the four quantities. Diathermic wall. If those be separated by a diathermic wall, the values of y and x and y dash x dash which changes spontaneously until an equilibrium state of the combined system is attained. The two systems are then said to be thermal equilibrium with each other. The thermal equilibrium is the state achieved by two systems characterized by restricted values of the coordinates of the system after they have been in communication with each other through a diathermic wall. Thermal equilibrium schematic representation is here. From this figure, it is clear that A and B are two systems separated from each other by an adiabatic wall, but in each contacts with a third system C through diathermic wall, the whole assembly being surrounded by an adiabatic wall. The two systems will come to thermal equilibrium with the third system. Here no further change will occur if the adiabatic wall separating A and B is then replaced by a diathermic wall. The second figure is shown. Here if instead of allowing both the systems A and B to come to equilibrium with C at the same time, we first have equilibrium between A and C and then equilibrium between B and C. And then when A and B are brought into communication through a diathermic wall, they will be found to be in thermal equilibrium. From the figure, second figure, here A and B are in thermal equilibrium with each other, then together A and B, A will thermal equilibrium with C and B will thermal equilibrium with C. Here comes the zeroth law of thermodynamics. Zeroth law of thermodynamics states that two systems in thermal equilibrium with a third are in thermal equilibrium with each other. The zeroth law is concerned with the thermal equilibrium of the systems. Two systems are in thermal equilibrium to mean that the two systems are in states such that if the two were connected through a diathermic wall, the combined system would be in thermal equilibrium. Next, we can see the importance of zeroth law of thermodynamics, concepts of heat and the temperature. The equation of state for a system can be written in the form phi of x comma y is equal to c. Here x and y are the thermodynamic coordinates. Consider we have several gaseous systems in thermal equilibrium with each other. Then phi 1 P1 V1 is equal to phi 2 P2 V2 is equal to phi 3 P3 V3 is equal to T. The numerical value of each of these function is same and define the temperature. It is the property of the thermodynamic system that is responsible for thermal equilibrium. Temperature is thus the level for thermal intensity and is a K factor in determining the direction of flow of heat. Next, we discuss variables and indicator. The variables defining a thermodynamic system are of two types: extensive variables like volume V, internal energy, which are proportional to mass. Then intensive variables like pressure P and temperature T, which are independent of mass. The interrelationship in a quasi-static process can be represented by curves or diagrams drawn with the help of a device called indicator diagram. One such example is a PV diagram. In PV diagram, pressure P is drawn along the y axis and volume V drawn along the x axis. One such indicator diagram in PV diagram traces for different states of a process in a thermodynamic state of the system. Then quasi-static process. During a quasi-static process, the system is all times infinitesimally near a state of thermodynamic equilibrium, and all the states through which the system passes can be described by thermodynamic coordinates referring to the system as a whole. An equation of state is valid therefore all these states. Quasi-static process is an idealization, that is, it is applicable to all thermodynamic systems. Then we can show what is work done in quasi-static process. In different processes, what will be the work done? Here first process, non-cyclic process. Consider a gaseous system. The gas in the cylinder undergoes a change in pressure and volume at constant temperature. Let the pressure and volume of it are changed quasi-statically from a state represented by a point A to another state B. From this figure, it is clear that A is the first state and B is the final state. Here pressure is drawn along the y axis and volume is drawn along the x axis. So, it is a PV diagram, it is an indicator diagram. If the pistons moves through an infinitesimal distance, an infinitesimal amount of work is done by the gas and is given by delta W is equal to PA dx is equal to P into dV. Here A dx is equal to dV, where A is the area of the cross section of the piston. The work done by the gas during whole expansion from a volume is W is equal to integral A to B delta W integral V1 to V2 P dV, which is equal to entire area AGHB under the curve AB. Work done during isothermal process. Here we take 1 kilogram of perfect gas and it is allowed to expand very gradually under isothermal conditions, that is, temperature remains constant throughout the system. The initial and final state be represented by points A and B on the PV diagram at temperature T. The work done by the gas during the whole expansion is W is equal to integral A to B delta W. Here as we show before slide, is equal to integral V1 to V2 P dV. For a perfect gas, PV is equal to RT. Here PV is equal to RT is the gas equation. W is equal to RT integral V1 to V2 dV by V. Let us see substitute for P. Then we get RT log V2 by V1. Then work done during an adiabatic process. In such system, no exchange of heat is allowed. Here 1 kilogram of perfect gas be allowed to expand under adiabatic conditions. Work done is equal to integral V1 to V2 P dV. PV raised to gamma is a constant K. This is the adiabatic gas equation, and here gamma is given as Cp by Cv, where Cp is the specific heat of gas at constant pressure. Specific heat of gas at constant pressure is defined as the quantity of heat required to raise the temperature of unit mass of gas through 1 Kelvin when the pressure be kept constant. Here W is equal to integral V1 to V2 K by V raised to gamma dV. Here we substitute pressure. Pressure is in the previous equation, PV raised to gamma is a constant K. Then P is equal to K by V raised to gamma. By substituting the value of P in the equation, we get K by 1 K divided by 1 minus gamma into V2 raised to 1 minus gamma minus V1 raised to 1 minus gamma. The final expression we get work done is equal to 1 by gamma minus 1 into P1 V1 minus P2 V2. Then work done in isobaric process. If the pressure of a system be kept constant, the process is said to be isobaric process. In isobaric process, the PV diagram will be horizontal line parallel to volume axis. The quantity of heat supplied to the system will result in an increasing temperature as well as increase in volume. So that for 1 kilogram mole of gas, delta Q is given as Cv dt plus P dV. Here P dV is equal to R dt from the ideal gas equation. Then we substitute for R is equal to Cp minus Cv, we get Cp dt. Here R is the universal gas constant for 1 mole of gas. Then we came work done in isochoric process. If the volume of the system is kept constant, the process is isochoric. Here the PV diagram will be vertical line parallel to P axis. Here the external work done is 0. Concept of path and point functions. The area under the curve depends on the shape of the curve. For same endpoints A and B, we can have several different curves and hence have different area. The work done in changing the parameters in diagram can be represented by the area under the curve. It follows that the work done by a system depends not only on initial and final states, but also on intermediate states it passes through, that is on the path. Work done depends on the path. Some properties of the thermodynamic system such as internal energy, entropy depend only on the initial and final state of the system. These are unique functions of the systems and have nothing to do with the path. such characteristic functions of the system are point functions. Then work. If a system undergoes a displacement under the action of a force, work is said to be done. If a system as a whole exerts a force on its surroundings and a displacement takes place, the work that is done either by or on the system is called external work. When the external force acting on a thermodynamic system is in the same direction as the displacement of the system, work is done on the system. The work is regarded as positive. When the external force is opposite to the displacement, work is done by the system, then the work is regarded as negative. Then internal energy of a gas. If a system is caused to change from an initial state to a final state by adiabatic means only, the work done is the same for all adiabatic paths connecting the two states. Whenever a quantity is found to depend only on initial and final state and not on the path connecting them, an important conclusion can be drawn. There exists a function of the coordinates of a thermodynamic system whose value at the final state minus its value at the initial state is equal to the adiabatic work in going from one state to the other. The function is known as internal energy function. Denoting the internal energy function U, we have W adiabatic is equal to UF minus UI. Here UF is the internal energy in the final state, UI is the internal energy in the initial state. The signs are such that if positive work is done on the system, the energy increases. Then what is an internal energy function? The physical interpretation of the difference of internal energy. That is, what is the physical interpretation of UF minus UI? Here UF minus UI represent the change in energy of the system. It states that there exists an energy function, the difference between the two values of which is the energy change of the system. The internal energy is a function of only two of the thermodynamic coordinates. Very often the exact form of the function is unknown. If the coordinates characterizing the two states differ from each other only infinitesimally, the change of internal energy is du, where du is an exact differential. Exact differential is of the actual function. Then mathematical formulation of first law of thermodynamics. The first law of thermodynamics states that when a system and its surroundings are at different temperature and on which work may be done undergoes a process, the energy transferred equal to the difference between the internal energy change and the work done is called heat. Denoting the difference by Q, we have the equation Q is equal to UF minus UI minus W. That is the difference between the two internal energies and work. UF minus UI is equal to Q plus W. When heat enters a system, the equation becomes positive, that is Q is positive. When heat leaves a system, the equation negative, that is here heat is negative, Q is negative. The three related ideas connecting the first law of thermodynamics. First one, the existence of an internal energy function. Second, the principle of conservation of energy. Third, the definition of heat as energy in transit by virtue of a temperature difference. The heat engine. It is a device that converts heat continuously into mechanical work. The three parts of the heat engine are: first one, a source of heat of infinite thermal capacity maintained at a constant high temperature. Then a sink. A sink is an infinite thermal capacity maintained at a lower constant temperature. There must be some substance through which heat is absorbed from the source and rejected to the sink. The substance is called working substance. The ratio between the amount of heat converted into useful external work and the amount of heat absorbed from the source is the efficiency of the heat engine. Here the work is given as work is equal to Q1 minus Q2, where Q1 is the amount of heat absorbed from the source and Q2 is the amount of heat rejected to the sink. Then efficiency of the heat engine is given as efficiency eta is equal to Q1 minus Q2 divided by Q1, where Q1 is the quantity of heat absorbed from the source and after performing useful work, remaining quantity of heat Q2 is rejected to the sink. Here the figure shows the source T1, a non-conducting platform, sink T2. The Carnot engine. In 1824, the scientist Sadi Carnot introduced this concept. Here the main parts of the Carnot engine are a cylinder with perfectly non-conducting walls but with a perfectly conducting bottom fitted with a perfectly non-conducting and frictionless piston. Second one, a heat reservoir or source of heat of infinite thermal capacity maintained at high temperature T1. Then a sink of infinite thermal capacity maintained at a lower temperature T2. A non-conducting stand where the cylinder can be transferred without friction. The figure shows the Carnot cycle. In order to obtain a continuous supply of work, the working substance is subjected to the following cycle of quasi-static operations. First, the cylinder is placed on the source and is allowed to undergo a quasi-static expansion. Then the thermodynamic coordinate become P2 V2 from their initial value P1 V1. The work done in the process is represented by the area under the curve AB. The quantity of heat absorbed Q1 is equal to integral V1 to V2 PdV. Here substitute for pressure RT1 log V2 by V1. Then second, the cylinder is now removed from the source, it is placed over the insulating stand. Gas is thermally isolated and is allowed to undergo an adiabatic expansion at the expense of its internal energy till temperature falls to T2. The work done is given as W2 is equal to integral V1 to V2 PdV is equal to R into T1 minus T2 divided by gamma minus 1. Third, the working substance at C is unable to perform work because the pressure P3 is very low here. Hence, it is brought back to the initial state A. For this, the cylinder is kept on the sink and the piston is moved so that the gas is compressed. The heat produced due to compression passes to the sink. This operation is represented by the isotherm and the work done is equal to heat rejected minus Q2 is equal to integral V3 to V4 PdV is equal to RT2 log V4 by V3. Fourth stage. At this stage D, the cylinder is again removed to the insulating stand and compressed adiabatically so that the initial state is attained. The work done is W4 is equal to integral V4 to V1 PdV is equal to R into T2 minus T1 divided by gamma minus 1. Then clearly the total work done by the gas is given as Q1 minus Q2, where Q1 is RT1 log V2 by V1, Q2 is minus RT2 log V4 by V3. So, the expression becomes RT1 log V2 by V1 plus RT2 log V4 by V3. Then what is the relation between V2 by V1 and V4 by V3?
From equation number 1, Q1 minus Q2 is equal to RT1 log V2 by V1 plus minus of RT2 log V3 by V4. So, substituting the equation number 4, that is V2 by V1 is equal to V3 by V4, we get the equation number 5, that is Q1 minus Q2 is equal to RT1 log V2 by V1 plus minus RT2 log, substitute here V3 by V4 which is equal to V2 by V1. So minus RT2 log V2 by V1, then taking the common term outside the bracket, that is R log V2 by V1 taking outside, we get Q1 minus Q2 is equal to R into T1 minus T2 log V2 by V1. That is equation number 5. Then the efficiency of the Carnot engine is denoted as eta, which is equal to, by definition, which is equal to Q1 minus Q2 divided by Q1. Then substitute the equation number 5, that is Q1 minus Q2 in the efficiency equation. Then then the value of Q1, which is equal to RT1 log V2 by V1 in the efficiency equation, we get efficiency eta is equal to R into T1 minus T2 log V2 by V1 divided by R T1 log V2 by V1. That is efficiency eta is equal to T1 minus T2 divided by T1.
Here the efficiency of the engine depends on T1 and T2, that is temperature of source and temperature of sink. It is clear from the above result that the nature of the working substance which is undergoing the Carnot cycle has no influence on the efficiency of the Carnot engine. The essential characteristic of a Carnot engine is that it is reversible and operates between two reservoirs. The superior efficiency of the Carnot cycle is due to its absorbing all heat at the highest temperature and rejecting all heat at the lowest temperature. Another important point is a Carnot engine is independent of the working substance of the system. Let me conclude the session. Today we have discussed some basic concepts in thermodynamics, the zeroth law of thermodynamics, the importance of zeroth law of thermodynamics, the first law of thermodynamics, the working of heat engine. Hope the session was useful for you. See you next time. Until then, goodbye.